All right, good morning, everybody. Yesterday, a couple of students asked me if I could either print out a few pages from yesterday's presentation or email the pages to them, and I thought it would be probably easier for me to just go through a quick 4 or 5 minute video describing the content of those pages. When we talked yesterday about the domain theory of magnetism, basically the domain theory of magnetism says that something is a magnet because it contains within it a bunch of tiny, tiny microscopic magnets that are arranged in a particular way. And each of those tiny, tiny microscopic magnets is referred to as a magnetic domain. So we have 3 diagrams up here. The diagram in the top left is the diagram showing what's happening or what the state of the domains is inside of a magnet. Now remember, a magnet is something that has a north and a south pole, and it is also considered to be a magnetic material. Inside of this magnetic material, which is a magnet, are all of these microscopic domains. I've only drawn inside of the magnet maybe 10 or 12 of these, and that certainly doesn't do it justice. There could be maybe millions of these little tiny microscopic magnets or magnetic domains. But each of the domains has a north and a south pole. And as a result of each domain having a north and a south pole, the magnet itself ends up having a north and a south pole. So the north pole of this magnet that I've drawn is on the right-hand side, and the south pole is on the left-hand side. And what makes that material a magnet is that the domains are aligned and they're locked in place. They're all oriented in the same direction. Whereas when you take a look at the diagram below, which is the diagram showing the magnetic domains that exist inside of a nail is not a magnet, but it is considered to be a magnetic material. And the reason it's magnetic is because it has magnetic domains that are able to move around. And that's the key difference between the nail, which is magnetic, and the comb, which I have a diagram of on the right. In the comb, plastic, which is what the comb is made of, is not a magnetic material. So even though you could argue that inside of the comb are magnetic domains, not only are the domains not aligned in the comb, they're not able to align. Whereas the magnetic material, the nail in the top left corner, those domains are not aligned, but they are free to move. So the reason why the nail is not a magnet, even though it's magnetic, is the domains are not aligned. The reason why the comb is not a magnet is because the domains are not aligned, but there's the additional condition that in the comb, the domains can't align, and that's why it's not magnetic at all. All right, if we take a nail, and the nail diagram is on the right-hand side of the screen, and we bring towards it a magnet, all of the domains in the nail will be influenced by the magnet that we bring in to the vicinity of the nail. So when I start to bring the south pole of the magnet towards the nail, all of the domains in the nail are free to move around, so the north pole of each domain in the nail is going to be attracted to the south pole of the magnet that I'm bringing in from the left. And the result is that I get a nail which now has all of the domains aligned. And since the domains are all aligned, the nail is a magnet. We refer to this magnet as a temporary magnet. It's not a permanent one. And the reason it's not permanent is if I remove the magnet on the left, those domains over time will start bumping into each other due to molecular motion, and they're going to randomize again. So they're going to not be aligned after a period of time. It may take a little while, but eventually the nail is going to go back to its original state. Since the nail right now is a magnet, it's a temporary magnet, and it has its north pole closest to the south pole of the magnet we brought in to this region of space, there is going to be a magnetic force of attraction. The south pole of the magnet will attract the north pole of the nail, which is a temporary magnet. If we were to bring towards that same nail the same magnet, but instead we turn the magnet around so the north pole of the magnet is going to come in from the left, then what's going to happen is the domains in the nail will again be influenced by the magnet being brought close, and all of the south poles of the domains in the nail will be attracted to all of the north poles of the domain in the magnet. In other words, the south pole of the nail is going to be attracted to the north pole of the magnet. So you're going to get a force of attraction. And this explains, by the way, why a nail will be attracted to a magnet no matter the orientation of the nail or the magnet. If I were to bring a south pole in towards a nail that was oriented vertically, then what's going to happen is all of the domains will flip over, and the north pole of each domain in the magnet, the north pole of each domain in the nail will be attracted to the south pole of the magnet, and the end result is that you get the nail being a temporary magnet, but the side of the nail on the left is a north pole, and the side on the right is a south pole. So it doesn't have poles at the ends, it has poles on the sides. The bottom line is the north pole of the nail, which is the left side of it, will still be attracted to the south pole of the magnet, so you're going to get a magnetic force of attraction. So I hope that helps you out with understanding the domain theory of magnetism and the difference between temporary and permanent magnets, and why magnetic materials are magnetic materials, and also why non-magnetic materials are not magnetic.